In this video, we'll be learning how to interpret function notation so we can add, subtract, multiply, or divide functions. So on the screen here, you're going to see a table that consists of what function notation with operations on functions looks like. So I'm just going to walk you through what they look like and then what they're going to ask us to do. So for this first one here with addition, basically what we're doing is we're taking two different functions, f of x and g of x, and adding them together. And how we'll write that sometimes with function notation is we'll put inside of parentheses f plus g, signifying we're going to take function f plus function g. Both of them are in terms of x. So you can see that this notation here, f plus g of x, is basically just a fancy way of saying function f plus function g. Now when we add these together, say we have this example here, all you're literally going to do is add those two functions together. Notice we have function f plus function g. And for this particular function set, all we're going to need to do is add like terms. So for every function that we're adding, subtracting, multiplying, and dividing together, it's going to be a different process because you have to look at the functions that you have and decide how you can simplify it further. In this case, it consists of just adding like terms, so we ended up with 10x plus negative 2. Now if we move on to look at subtraction, you'll notice that the notation is very similar. So here we have f minus g of x. So you can see we have the f minus g in parentheses to signify that we're taking f of x first and we're subtracting g of x from it. Now this one is a little bit easier to make some mistakes on. You have to make sure that you subtract both terms in g of x. So often I will actually write down the f of x. So here we have 4x plus 3 minus, I'll then take what g of x is equal to, which is 6x minus 5, all in parentheses. To remember that I need to subtract and change the sign of both. So really what's happening here is we're basically multiplying both of these by -1, so they turn into a -6 and then a positive 5. But then from here, it's just adding like terms again. So we end up with -2x plus 8. Now from here, multiplication notation, again, it looks very similar. You'll notice that we have f times g of x, and here we'll notice that we're multiplying the two functions together. Now for this, I always suggest utilizing parentheses to start so that you don't miss any key multiplications. So you'll notice that's what I did here to start. I took f of x times g of x, and I noticed in doing that in this particular situation, I had to do big distribution. And so I did. I took everything in the first parenthesis times everything in the second parenthesis. And you can see my work here to get my final answer. And then division, for this particular set, is pretty easy. It's not always this simple, but for this particular set, we're going to take f over g of x. So we took function f, put it in the numerator, function g, put it in the denominator, and in this case, we don't yet have the tools to simplify this function. There will be functions that we can use, different strategies we've learned to simplify it further, but in this case, we don't have those tools yet, so we just leave it as is. So let's practice interpreting and completing a couple of examples. So here we can see that we're adding together functions f and g of x. So I'm going to utilize these two functions here, and I'm simply going to add them together. So this is going to equal f of x, which is 3 squared of x plus 8, added together with -10 squared of x minus 5. And then from here, just looking at the problem, I notice I have some constants, so I can definitely add those together. And then with square roots, I notice that I have to have like square root parts because they add together like terms. Well, in this case, they do. They have a square root of x, so I can simply add together my coefficients there to get -7 square root of x plus 3. And that's it. It doesn't combine together further because remember, those square roots act like terms. You have to have matching square root parts in order to add them together. For example 2, I'm going to take h of x and subtract p of x from it. So here, if we start off with h of x, we have 3x cubed minus 2x squared plus 5. Then I'm subtracting, and I'm going to put it in parentheses so I don't miss a sign change. X cubed minus 3x squared plus 4x minus 2. Now I know here I have a negative 1 to distribute out. So we have 3x cubed minus 2x squared plus 5. Then we have minus 1x cubed plus 3x squared minus 4x plus 2. So all I'm looking to do here is combine like terms together. So I notice here that two of my terms contain x cubes, so those become 2x cubed. Then I have two terms that contain x squared, so that becomes plus 1x squared. This is the only one that contains an x, so I'm going to leave it by itself. And then I have my constants at the very end that add together. So those are two examples, one that contains addition and one that contains subtraction. So you'll notice here that our two examples look a little bit different. First, we are going to find f times g of x and h divided by p of x, but then we're also going to evaluate those functions for specific x values. So we're actually going to take that function then and apply it with an actual x value. So here, we're going to start by multiplying the two functions together. So I have x squared times the square root of x. And it might look like I can't simplify that further, but using my knowledge of roots and exponents, I know that I can rewrite this to be x squared times, this is really x to the power of, this is really a 1 inside of there with x, as x's exponent, so it's 1/2. So I know that the square root of x can be rewritten as the fractional exponent 1/2. I then also know, just based on my experience working with exponents, that when I have common bases here, I can actually simplify this to be x to the power of 2 plus 1/2. Now I can give x an actual numerical exponent by simply adding together 2 plus 1/2. If I turn 2 into a fraction, multiply numerator and denominator by 2, I'll get my common denominators. So I have 4 over 2 plus 1 over 2, which is 5 over 2. So in its most simplified form, f times g of x is really x to the power of 5 over 2. Then from here, it's saying we want to evaluate the function when x is equal to 9. So what that's asking us to do is now take x, replace it with 9, and evaluate. So from here, we're going to take 9 to the power of 5 over 2. Well, I know that the square root of 9 then to the power of 5 is how I can rewrite that. So that becomes 3 to the power of 5. And if I evaluate that with my calculator, 3 to the power of 5 is 243. So here I was able to multiply those two functions together and then evaluate it when x was equal to 9. Now if we take a look at this next example here, we're being asked to take h of x, which is 6x, and divide it by x to the power of 3 over 4. Now, this might look like we can't simplify it further, but using what we learned about having common bases within fractions, I know that because there's an x in the numerator and an x in the denominator, that I can actually simplify this further. So I'm going to put x to the power of 1 in the numerator, and then because I have common bases here in the numerator and the denominator, I know that I can simplify those by subtracting their exponents. So if I take 1 minus 3/4, I can actually subtract that, turn that into a fraction, get common denominator, so it's 4 over 4 minus 3 over 4. So that gives me an exponent of 1/4. Now remember that that x to the power of 1/4 is going to go in the numerator because 1 was larger than 3/4. So my simplified function in this particular case becomes 6 times x to the power of 1/4. So that's what this function notation asks us to find. Take h of x, divide by p of x, and simplify as much as we can. Now we need to evaluate this for when x is equal to 16. So now we're going to replace x with 16. So we have 6 times 16 to the power of 1/4. Now if we think about our order of operations here, we know that it becomes parentheses followed by exponent. So I need to evaluate this exponent first. So I get 6 times, this becomes the 4th root of 16. Well, the 4th root of 16 is 2 because 2 to the power of 4 is 16. So 6 times 2 is equal to 12. So here we were able to divide two fractions and simplify, and then evaluate that function for when x is equal to 16.